Welcome back. We now want to continue our discussion with the topic of discriminative models for classification. So let's just recap what we did so far. We modeled so far the posterior distribution P of y conditioned on x based on our generative process, first generating y and then generating x. So instead of modeling this posterior distribution via this Bayes rule, why don't we just model this distribution P of y conditioned on x directly? And this is the core idea of discriminative models. We directly model this distribution. Okay? So here a more detailed look. So what we did in the LDA approach, for example, we derived our model and then we looked at the distribution for class label 1 or class label 2, 0, given the x. And then we have seen that this follows a very specific form. It was a sigmoid function in a binary case, and here we had this linear term wx plus the offset. And what we have seen is that in the LDA, these w's, they were somehow hard-coded. They followed from the maximum likelihood estimate, for example, of the mu and sigma matrices, right? And this was really just some closed form how we can compute it. And the core idea is now, why do we have to follow this specific closed form? So why do we just use w to be equal to some equation? Why don't we just treat w as a free variable we can optimize over? Okay? And that's the core idea of this discriminative model. So we again assume, for example, that our probability of being class label 1 follows this function, but now these two w's here, we can choose them arbitrarily, not just following this restricted rule, so to say. Increasing the flexibility of our model, simply speaking, or the parameter space, right? Because we can choose any w or w0 we have in mind. And indeed, this is what we do in this first approach, which is known as logistic regression, where we assume that, similar to an LDA approach, our label, our class label, follows a Bernoulli distribution in a binary classification task. So it's a 0 or 1 flip, so to say, we are doing, where the parameter here of this Bernoulli is, as in LDA, our sigmoid and this linear term. Again, with the crucial difference that now the w and the w0 are free parameters we can arbitrarily choose. Okay, so this simple model is known as a logistic regression model. This is a very fundamental discriminative classifier which you more or less encounter in different places in machine learning. So here again, just as a recap, what we have seen before, right? The sigmoid is this function here. It's like this S-shaped function which maps between 0 and 1. So this gives you back a probability or a score between 0 and 1, which can be interpreted as here this parameter of the Bernoulli distribution, so giving you the tendency whether it's class 0 or class 1. And as I said, this is called logistic regression. So if you want to draw the generative model of this process, it looks more or less like what you did in a standard linear regression, the probabilistic view of linear regression, because now we do no longer treat x as a random variable, but x is like some deterministic input, and this x affects our y, which is our random variable. And of course, we have the parameters here w and w0, which are also affecting y. And of course, y is observed because we're here in a supervised learning setting. Okay, so note a crucial difference from the generative perspective. There we first had the y, and then below we had the x, right? It flows from y to x. Now y is here above. It's some deterministic input. It's no longer the outcome from a random process, and this x affects the y. Okay, so this is also why when now talking about this y, technically here we're computing the likelihood later on, right? Because the y is here now in the lower part, we are computing the likelihood, and before this was the posterior distribution, right? We had like a distribution on x and then a distribution on y, and we computed here this posterior distribution. Here you can, if you want to give it a name, this is more like the likelihood, which we later on look at. Okay, so that's now the probabilistic graphical model we are considering here. And again, see the relation to standard probabilistic linear regression we talked about. There you also had the input, the parameters, and then we had here the continuous target. So this view is more aligned to the regression setting we talked about. Okay, so this is the setting, right? This is our probabilistic model, and I already mentioned the term likelihood and so on and so forth. So how do we now find these parameters? One idea, of course, is to maximize the likelihood of this distribution. Okay, so here are many points you should already be aware of. Just for completeness, we added them here. Of course, as before, we can absorb the bias term into our data representation by adding a constant 1. So usually we just use this notation and not this. We don't explicitly mention the bias term, but this is all what you should be aware of already from the previous videos. Okay, and here's what I also just said. So how do we now learn these parameters? We can learn these parameters by maximizing the likelihood. So the first step is, of course, to write down the likelihood function. And you all know how to do this because, again, we have here an IID setting. We assume that the instances are specifically independent, meaning if we look at the overall likelihood, right? So we have y, the observed data, conditioned on the parameters on the input data x. It can just be written here as this product over every sample we have at hand. And here we have our individual terms, right? P of y conditioned on x and w, what we have seen before, which is here this distribution. Here again, we use this trick with this indicator, which we use already a couple of times. So y is either class 0 or class 1, meaning if we are in class 1, we are using this probability so that the label is class 1, right? And here, this will kick in if y equals to 0, right? Because then here we have a 0, here we have 1. And then we have the probability of here being class 0, which of course is 1 minus the probability of being in class 1. Okay, so this is simply, again, this trick with this exponent as an indicator. And then finally, we can rewrite this in terms of the actual function, because we have assumed that this here follows our simple sigmoid, right? So this is sigmoid linear function, the bias term observed to the power of the indicator, and then 1 minus the sigmoid to the power. Okay. So again, here the point. So now be careful just from the wording. So to say that this is now a likelihood function, because here we have the y. From the lower part, we are measuring the likelihood of this data, of this observed data, given the rest, right? But before, if you want to call it, give it a name, before this was here more like the posterior distribution, because we've applied Bayes' rule to get from the likelihood of x, right? Because again, so here in the LDA model, it looked like this, right? We had the y as a prior, and then we had the x here, and then we here derived the posterior for y, which ended up here. So this is why we call it here posterior, and why we call it here in this model, this function is now called the likelihood, okay? Because it's a different probabilistic model. Okay, in one case, y is in the lower part, in the other case, y is in the upper part. And this is indeed the crucial difference, right? The first one was this generative model where we generate or can generate the x's, right? And here in this model, of course, we can no longer generate x, right? Because x is just some deterministic input. It's not the outcome of a random process. Here we can only generate, so to say, the y's, the ones the label we want to predict, but we can't use it for generating data. Okay, so back to the learning. Right, so we want to learn these parameters using standard maximum likelihood estimate, for example. So we have here again our samples given. We have written down the likelihood function, which looks like this. And now we can do the same trick as we did for the regression setting. So instead of maximizing the likelihood function, we aim to minimize some error function, which we just do here. And you know how this works. So here's our likelihood. We usually look at the log and we take the negative of it. So the error function we want to minimize is called the so-called negative log likelihood again. Okay, this is what we want to minimize. So why I'm showing this here again is because this negative log likelihood function has a very prominent name in the machine learning community, specifically in neural network. Because if you again write out what this means, right? Be careful, now we have here the log. If you look at this slide, right, we take the log here, so to say, in front. So all the products become a summation and the exponents go to the front, right, based on the log rules. So we see that this negative log likelihood simply boils down to the following function, which is, of course, minus sum over all the data instances we have. Here we have the indicator, which class does this instance belongs to. We have here the log term, 1 minus the indicator, and again the other term. Okay, so be careful again, y is given, right? It's a supervised learning setting. So what we have as input is the x and the y. This is given by the training data. So what we see is that on one hand, either this kicks in, if this is class 1, or this kicks in, if this is class 0. Okay, So again, why I'm showing this is because this function here, this loss function, has a specific name in the machine learning community. It's called the binary cross-entropy. So you will see this term a lot when looking, for example, in different papers or in the internet. So this loss function, this error function we aim to minimize is the so-called binary cross-entropy loss. Okay? And here again, you see the goal which we try to achieve. We want to minimize this binary cross-entropy loss over the parameters, of course, and this will lead to the optimal parameters we're interested in. And as in the regression setting, these parameters are not just arbitrary. They are not the binary cross-entropy optimal parameters with respect to binary cross-entropy are not just arbitrary, but they correspond to the maximum likelihood estimate based on the probabilistic model we just picked, based on the idea that the y come from a Bernoulli distribution with the sigmoid and linear function model. Okay, so that's all, right? So this is how we can learn, or how we can now set up a so-called discriminative model where we immediately join the distribution P of y conditioned on x, and then it turns out to just minimizing this function. The drawback here is, and this is a big difference to the LDA approach, for example, is that we do no longer have a closed form. So in the LDA, we had this W, and that was just a simple form based on sigma and the mu's, right? And the sigmas and mu's were also just easy to derive. So the maximum likelihood estimates in the generative models were easy. So also the W's were easy to derive in closed form, even analytically in some equation. Here, however, this is not possible. So based on this general form I just have shown to you, and we don't get a closed form estimate. So this can't be computed in closed form, unlike to regression, for example, where we had this pseudo-inverse involved, this normal equation. So here, no closed form, unfortunately, no analytical form available. But as a spoiler, so to say, for the next lectures, we can solve this with optimization, for example, numerically. So instead of having an analytical optimal solution, we use numerical optimization techniques to find this, or to approximate at least this optimal W star. For the moment, however, let's just assume this is given. Okay, so in the next videos we talk about how to find it, but now we assume it's given and we can solve this maximum likelihood estimate. Okay, just also another remark here. Of course, in this setting, similar to regression, for example, you can of course now also add a regularization term. Since we now have here our negative log likelihood, or the cross-entropy loss, of course we can again try to avoid overfitting by adding regularization. We add like an L2 penalty, for example. We have the corresponding regularization strengths. And not surprisingly, this would correspond to solving for a map estimate. Meaning we add in addition a prior distribution, what we expect to see for this weight, so to say, our prior knowledge about the weights. If we pick a specific Gaussian prior, we would have again here an L2 regularization. And as before, we can then control the flexibility of the model. If this is very low, small, this essentially disappears. We just focus on the fit, and this might overfit or might not. I mean, here it's not really complicated because it's just a linear function. But if we make this larger, we are focusing on small weights. We make the model less flexible. We prevent overfitting, but we might end up in this regime of even underfitting. Okay, and then of course, also we can generalize this logistic regression setting to a multi-class logistic regression, to more than 2 classes. And this follows the same principle as before. So we don't use the sigmoid function anymore, but we're using this softmax function, or put differently, we are directly modeling this distribution. We say that the probability for class being labeled as class C is like e to the power of this linear term normalized by all the other terms. Or in the more compact form, if we're using the softmax, we can simply write it as softmax applied to W matrix times X, potentially again some bias if we want to add it. This is usually what you see in the standard neural network literature, that we have this explicit bias. But important, this is a matrix, this is a vector, so this becomes a vector, and then we apply the softmax, which just maps it to some probability distribution over all classes. Okay? So again, how does this relate to LDA? It's more or less the same function, right? So this was also what we used in LDA. We had this simple multi-class setting, right, where we apply the softmax now. Again, the only difference is that in LDA, this and this here, this was somehow like predefined by the mu's and sigmas we have learned from this MLE estimate of this generative process. But now this W and B here are free variables, right? We can pick them arbitrarily. And again, this of course is a larger choice, so to say, we can make. We have a larger space we can optimize over. So we might be more flexible in our model here. Flexibility here, and let's be just careful when saying this. This, of course, only means what kind of parameters we can pick. Right here, we do not pick it based on this closed forms we have seen before, but we can just pick any matrix and any vector. But of course, the solutions we are getting will still lead to a linear decision boundary. Okay, because these here are still linear functions, or here in this case, it's even more easy to see. Here in this very first example, scrolling back here, of course, this is still a linear function. So even though we make these now free parameters we can freely optimize over, the solution will always be a linear decision boundary. There is no way around it when we don't change here this inner term. It's just that we can find other parameters. The parameters are not fixed. Or put differently again, right? So what we have seen in this LDA, for example, is that the decision boundary is always like here in the middle, so to say. But here we have more flexibility. It could be the case that, for example, this here is some better solution. I mean, of course, as you can imagine, so for many scenarios, if the data is linear separable, this would, of course, be a good choice. But again, we have more flexibility to find the parameters. We are not limited to it. And specifically, why is this more flexible? Because in the generative models, we had to assume specific structure, for example, about the covariance matrix, right? In LDA, we had a shared covariance matrix, for example. Here, we don't assume anything about this covariance structure, about the data generation process, because we don't care about the data generation process. We just care really about the classification rule. So we do not have to make this assumption, and then potentially the final decision boundary we find might be better because the data might not follow what we have assumed in the LDA approach. So if the data, for example, is not like a Gaussian, but it has some other shape, like these two shapes, right? Then this solution might be better, and in general is better, because it does not pose these assumptions. Okay, so flexibility just relates here to the choice of parameters we can make. It's still a linear decision boundary, or here in this multi-class setting, these linear pieces. Okay, so then how does this loss look like for the multi-class setting? Right here, it's just the definition, so to say, of our model. The loss we can again write down by looking at the likelihood. It's also again straightforward. So here's our likelihood term. Then we have the overall negative log likelihood. We can just plug it in. And here we use some different notation. So before we had only this indicator saying class 1 or 0. Here we use some different well-known notation, which is the so-called one-hot encoding. So this YIC is either 1 or 0 based on the following idea. So for example, if some instance belongs to class 2, we put an indication, a 1 at position 2. Okay. If an instance belongs to class 4, for example, we would have the indicator 5 at position 4. Okay, so these vectors are called one-hot vectors or one-hot encoding because they are indicating encoding to which class this belongs to, and these are C-dimensional vectors if we have C classes. Okay, so every of our data instances, so to say, is labeled with these one-hot vectors. So this is why we can represent the labeling of the training data with this matrix. For every sample n, we have a C-dimensional vector, as given here, where the entry says 1 if the sample I belongs to class C and 0 otherwise. Okay, and this is again what we're just using here, right? Because only the term, the probability, is taken into account for sample I, which belongs to class C. Okay, we only are interested in the likelihood and the probability that this sample I belongs to class C because it has been labeled with class C. Okay, so this is why we have here this term similar to what we have seen before. And this final function, this loss function, this negative log likelihood in the general case has also a common term. This is just a standard cross entropy. So before we had the binary cross entropy, this is just a general cross entropy. Again, the loss is here this indicator, and then we always have this log of e to the power z term normalized by the other terms. Okay, so this is also a common loss you might encounter in all these deep learning frameworks. For example, you can pick a cross among different losses, and often the cross entropy or binary cross entropy is a good choice. Why? Because again, it corresponds to finding the maximum likelihood estimate of your parameter w giving the specific model. Okay, and this is actually all what we can tell here about this discriminative models. We have actually even seen that this is much simpler, right? We just say, okay, our label is following this softmax or sigmoid of a linear function, and that's all, and we just optimize these parameters. And at the end of the day, as I said, we will find like a specific hyperplane which separates these. And specifically in the discriminative case, we do not have to assume specific behavior of the data. So here again, this example, right? If these, for example, was your data, right? This is not really coming from a Gaussian. So assuming an LDA model is not good. And this is also the reason why this discriminative models often achieve better performance when we just care about the pure classification task, right? Because here the assumption of a Gaussian doesn't apply. Still, we are able to find a good hyperplane which separates these two, right? And this is indeed what we are just doing by minimizing this function. We are finding a hyperplane which separates these two because, again, what do we want to achieve? We want to achieve that. Let me show this actually here in this example. We want to achieve that all the training instances which are labeled as class 1, they should have here a high term, because then the likelihood that if we do a coin flip, very likely shows 1. While all training samples which are labeled with 0, they should have here a low term, right? Because then if we would do a coin flip, it will likely show 0, right? So this is the core idea. We want to make this to be sure that it's close to 1 for these samples and close to 0 for these samples. And we want to find these parameters that this is given by this line. So indeed, just more a bit of a discussion. So what you also see again is, of course, this is not a hard classifier, right? At every point, so if we want to, for example, do inference, we have here new x, right? So here comes a new x. We can, of course, plug it in into this equation. We get again a term, which could be, for example, I don't know, 0.4, right? So it should give this a score of 0.4, meaning it's only 40% likely being class red, but 60% likely being class blue. Okay, so this is again the advantage of this probabilistic models, which we also get for the discriminative approach. Okay, again, back to the summary then. So the discriminative models are often better for the pure classification because we do not assume any specific structure besides having a linear hyperplane here, a linear decision boundary, but the rest is completely free, so to say, and this is why they often work better. However, these generative models, they have some other advantages, okay? Why they might not work well if the assumptions are violated, as shown here. They often work well if the assumptions are true, okay? And then specifically, they also allow you to do other stuff. For example, they allow you to handle missing data. They allow you to detect outliers, and they allow you to, for example, use it in a so-called semi-supervised learning settings. So these are all points which we don't discuss here at the moment in detail, but there are many other benefits of these generative point of view. So just the outlier point. So what you could see, for example, how we have drawn it in the previous part of the video, we had here these two classes, for example, and we set in the generative point of view, if a new instance arrives, we check, okay, does it likely belong to class 0, blue? Yes. And to class red? No, less likely. However, we can also get a sample here, and then you see, oh, wait a second, this neither belongs to class blue nor to class red. So this is an outlier, right? And we can see this because this doesn't fit to these two distributions, right? We have the generative distribution, so to say, for blue, P of X conditioned on blue, and we have P of X conditioned on red, and we see that this does not fit either of these. This is something you don't get for a discriminative model, because the discriminative model does not tell you how well the instance X fits to your observed, to your given data, right? It just tells you how likely is a specific label, right? It doesn't make any statement about the likelihood of X, it just makes a statement about the likelihood of Y. So in a standard generative model, even if an instance is here or here, you will just get some score. You will just get a score, okay, probability 90% that this is class red, even though it's very far away from the red samples. And this is one very strong benefit of using a generative model. It can handle these outliers which do not belong to any classes, OOD detection, out of distribution detection, so to say. But again, if the assumptions do not hold, they might not work very well. And also, if you have very complex data, let's say images or graphs even, this is a very open research question, how actually a generative model looks like. Right? For numerical data, we have Gaussians, but how does it look like for images? How does it look like for graphs? So this is something we will cover in our advanced lectures, so feel free to watch these videos as well. But this is what we unfortunately can't discuss here. So this then indeed wraps up already this first part on classification. So we mainly talked here about linear classification, except naive Bayes, which was like a quadratic decision boundary. But specifically, you have seen these two views. Generative, with additional benefits we can have here, right? Take into account this figure again. And then discriminative, where we only model the distribution over the class label, where we don't model over X, but only over Y. We do not pose strong assumptions on the data, so for classification they often work better. But both at the end of the day have like found a hyperplane which we then can use in a probabilistic sense, in a soft way, so to say, to assign class probabilities, so label probabilities, so how likely is a specific image to be a cat, dog, or human to our corresponding input. And what was also important to remember are these two terms of learning and inference again, and this also of course applies to both of these models. Learning means we want to derive the parameters via maximum likelihood estimate, for example, and then inference is the task when we get a new sample, we want to infer the distribution over Y, for example, to make a prediction to which class it belongs. So with this, I want to end this first part. As usual, feel free to ask your questions online, and we'll see us in the next videos. Bye bye.